Hello guys, nice to see you. I hope you're doing well. Yesterday we had quite rough weather conditions.
Good afternoon.
Hello.
Where are you?
I'm in Nur Sultan on campus.
Oh, yes. It's
So it was not so bad in the southern part of Kazakhstan.
I don't know. I'm from North.
Okay. Yeah, I believe that many of you are distributed all over the country. By the way, is someone from outside Kazakhstan, from abroad? Yeah, looks like most are from Kazakhstan. So, yeah, I'm originally from Ukraine, but worked for years in Germany, United States prior joining physics department at NU. Okay, I believe that other people can join on the way. And yes, I mean, previous lecture, we had a short introduction in terms of understanding and defining what is electric charge and like some feature of material which defines how its electric interaction with other electrically charged objects. And we know that there are two types of charges defined as positive and negative. And later on, it was figured out that electric charge actually is quantized and it can change only discretely. So you cannot change electric charge by any amount you would like. So there is some minimum value of possible electric charge which can exist under normal conditions outside the atoms. Because so we usually deal with negatively charged electrons, and that is in absolute value. This charge is 1.6 10 to minus 19 Coulomb. So proton has the same absolute value of electric charge as electron, but it is charged positively. And there are some evidences of smaller electric charges like quarks, structural units of proton and neutron, which can possess some fractions of electric charge of this smallest electric charge of electron. However, they do not exist outside the nuclei, and that's why you cannot participate in charging some bodies and cannot participate in charge transport. So that's why it is not considered in the course of electrodynamics. yeah, in the model we have Q, yeah, it's E, so stands for electron, but there are different options how you can define these values. So we will definitely specify it in future. So obviously now we need to go to more quantitative description that allows us to calculate some forms of interaction between different charges. And these kind of experiments were carried out by Charles Coulomb, and he was using some torque scale to measure the interaction between 2-point charges. Like point charges means that we neglect with the sizes of these spheres on which charges were accumulated in comparison to the distance between them. And his experiments revealed that electric force, like absolute value of electric force, it is proportional to the product of absolute values of two charges which interact with each other, and reversely proportional to the square of distance between these charges. However, in order to get the real value for the electric force, you need to determine some constant, some prefactor which stands in front of this equation, and that is called Coulomb constant, T with subindex E, the K with subindex E, which is equal to 1 over 4 pi times epsilon 0. So pi is numbers 3.14, and epsilon 0 is a fundamental physics constant. It's equal to 8.854 10 to minus 12 Coulomb square divided by Newton times meter square. And based on this, we can write in a vector form, since force definitely, as we know from the previous course, it's a vector quantity, vector parameter. We can write in general form the equation, like Coulomb equation, which is electric force as a vector is equal to Coulomb constant times Q 1 times Q2 divided by R squared, and here is R vector, which is unit vector and defines the direction of the force. And this is the Coulomb law, which should be taken into account during solving many different types of problems in electrostatics and electrodynamics. So you should definitely try to remember it. And now let us define the direction of this Coulomb force, because so far we are talking about like absolute value, but we need to define how exactly these charges will interact with each other. It depends on the sign. So let us first consider some case of two positive charges. they are at some distance from each other, r. And we know that charges with the same sign, they repel from each other. And we also need to take into account that this the third law of motion, the third Newton's law, is working and should be taken into account when we consider electric forces. And in this case, let's call this one charge 1, this charge 2. So there will be some electric force from the charge 1 exerted on charge 2. Let's mark it as F12. And according to the third law of motion, there will be equivalent force, but directed in opposite, aligned in opposite direction. It will be force F21, so force originated from charge 2, which is exerted on charge 1. And they will be equal by absolute value. So we can write F1, 2 is equal to F2, 1. But in terms of when we consider them as vectors, they are equal to each other with a sign minus. So F12 vector is equal to minus F21 vector. If we have, for instance, case when we deal with positive and negative charges, which are located at some distance r, these forces will be, electric forces will be in going inwards because we have attraction, and they will also obey these conditions. Since we need to keep in mind that the third law of motion is working always. Also, what is necessary to highlight that if we have a system of electric charges and want to define what is effective force which acts on one of electric charges in this system, then we need to sum up all forces which are exerted on this particular charge from its neighbors. So in this case, we can write, let's say we have some charge indexed as 1. So this effective force which acts on this charge will be the sum of all forces exerted on this charge from neighbors. It will be F2, 1 plus F3, 1 plus so on plus Fn, 1. So in other form, we can write that this will be equal to the sum of I equals 2 to n Fi1 vector. So we need just add these vectors, sum up these vectors and define effective force. So maybe now let us consider some very general cases of or application of Coulomb law to make you feel better with doing some basic calculations, which include Coulomb law in the process. So let's go to another slide. And first, our example, let us consider some weight, which is hanging on some massless rope. So we have some mg. Then obviously we have some tension in the rope T. And let us assume that this body is positively charged with some charge Q. So it's positive charge Q. Then we have some mobile charge, also positive charge. Let's name this one Q1, and this will be Q2. So we can move this positively charged body, and the question we would like to answer in this case would be what should be the distance d between these two charges at which the tension in the rope will be reduced, will be twice reduced, so will be twice smaller than it was initially without considering charge Q2. So obviously it should be from above the charge Q1 because we have two positively charged bodies, so they will repel. Means that we need to align these charges in that way that the electric force will be directed upwards, opposite to the weight of the body, which is hanging on the rope. And that means that the absolute value of the electric force should be half of the tension, because we want to reduce it by half. And this obviously is equal to mg divided by 2. So we know we can apply now Coulomb law to calculate this electric force, the interaction between two positively charged bodies. And in this case, it will be, we can write either Coulomb constant or like Ke or 1/4p epsilon 0. And so permittivity of free space. So we will do both because it will help you to be more accustomed to deal with different conditions, because in different sources you may see this equation in the form of Ke or 1/4 pi divided 1 divided by 4 pi times epsilon 0. So let's go here for 1 divided 4 pi epsilon 0. Then we have Q1 times Q2 divided by R squared. Okay, so this is clear. We know that, sorry, and here the distance is given not by R squared, so we will replace it by D squared because we named it D in this case. So from here, we obviously can determine from this condition, we can easily calculate D. Let's go for D squared first, will be equal to 1/4 pi epsilon 0. Then we have 2 times Q1 times Q2. So we get this 2 from here, from this denominator. And then divided by mg. So we cancel out these 2. Then we have here 2 instead of 4. And also take square root in order to get the distance. So we have square root of Q1 times Q2 divided by 2 pi epsilon 0 times mg. Okay, so this is one of the very simple example how you can apply Coulomb law. Let's consider another one. Now it will take into account some rotational motion, like motion along a circular trajectory. So let us assume some, let's say it will be hydrogen atom. So you know that hydrogen atom consists of a proton and an electron which is circling around it. So this is negative electron. Let's name it P. This one will be E. So it moves, follows some circular trajectory. And our question will be, let's say we know the angular frequency, omega, of this motion along the circular trajectory. We know, obviously, charges of electron and proton. And based on this information, we would like to kind of estimate the distance, the radius of this orbit. So this radius is a question we would like to answer. So in this case, we need to consider that there are two forces which are acting. So this electron, for sure, this orbit is a stationary orbit. It doesn't change over time, so it stays in some equilibrium condition. So in this case, there will be two forces which should be taken into account. One will be, of course, the electric. So let's draw this electron here. And one will be directed toward the proton. It will be electric force because they have different electric charges. So there will be some attraction between them. And another force is due to this centripetal acceleration, like centrifugal force. Let's call it just F. Because of moving along the circular trajectory. So when we have curved trajectory, we always have some centripetal acceleration, regardless the fact that the linear velocity of the motion is constant. So just to remind you these basic features from the previous course. So we keep this in mind, and based on these two forces, they keep this electron in its position and doesn't allow this electron neither fall on this proton or just fly away from proton. There is one more force which acts between them. which we didn't consider yet. Do you have any ideas what we are still missing there?
Gravitational force.
Yes, exactly. So these guys possess some mass, and definitely if there is some mass, there is some gravitational force. However, as we mentioned also last time on our online lecture, gravitational force is like many orders of magnitude weaker than electric force, and in this case it just doesn't make sense to consider it because it's negligibly small. So then let us consider these two forces. So first one, we need to deal with mass of electron. So here we don't use any numbers, but just for your reference, should be like 9.11 10 to minus 31 kilogram. This is mass of electron, like free electron. Because later you will figure out that there are some effective masses of electrons in solid state materials when it is necessary to take into account the effect of surrounding, like this periodic crystal lattice on the way how electrons move, and that's why we deal with some effective mass of electron. But when electron is free, let's say in vacuum, far from other atoms, like some periodic structure of crystalline lattice, we deal with mass of free electron, which is this one. And this is true for any free electron. So there is some mass of electron. Then we need to, in order to calculate this force, we need centripetal acceleration. And since we know the angular velocity, so we need to express it in terms of angular velocity, it will be omega square times r, this radius of the curvature, which is unknown now for us. And now we equate this to the electric force. Electric force definitely we calculate based on the Coulomb equation, and this could be written as 1 over 4 pi times epsilon 0 q electron, big absolute values, and q proton divided by r squared. So we know that these two charges are equal to each other in absolute values. So we will replace it just by 4 pi epsilon 0 q squared divided by r squared. And from here, we already can put this r squared in nominator, like in the left side of the equation. So we will get r cubed. And after rearrangement, we get q squared divided by 4 pi epsilon 0 times me, electron mass, times omega squared. And in order to get the radius, we can write q squared 4 pi epsilon 0 electron mass omega squared in the power of 1/3. So this is how you approach this type of questions. Let's do one more a bit, which takes like a bit more of geometry into account, and then we will proceed further to the electric, to the concept of electric field. So,
sorry, can I ask one question?
yes, sure.
Why the centripetal force is not towards the center?
Oh, can you repeat, please? It was not good connection.
Why the centripetal force is not pointed towards the center?
Oh, it's centripetal acceleration is pointed toward the center, but the force which resulted is pointed to the opposite direction. So it's like centrifugal force. It will go to in opposite direction to the centripetal acceleration. And centripetal acceleration goes to the center of the curvature because of the change of the linear velocity vector, which happens while body with a constant linear velocity moves along the curved trajectory.
Is just mass centripetal, so it has to toward the same point was which is the acceleration, centripetal acceleration.
Yeah, I'm sorry, but it's really difficult to hear you. I hear only some parts of the words. Maybe you can try ask me a bit later. Maybe the internet will get better. Or yeah, your network bandwidth is slow. Let's wait a bit later. Maybe it can work better. Can come back to this question. Okay. So let us consider some system of two charges attached to like hanging on some ropes with a length of L, capital L, and these are positive charges Q plus Q plus Q. They are equal to each other. And here we have, from the center, we have some distance A. And we want to figure out the values of these charges, like the Q, when we know these angles. So this is theta, and here is also theta. So in this case, what we need to take into consideration, there will be some like two forces which act on each of the will act on these charges. So it will be some weight of the object, mg, and some electric force. So since they are of the same sign, they will repel from each other, and that's why they form this kind of triangle. So here is electric force. So there will be some resultant force, and this is actually compensated by the tension. Oh, sorry, it's not. It's tension in the rope, because the system is in equilibrium conditions, so these charges do not move anywhere. So in this case, we can set some system of coordinates. Let's have we have some x, y, and taking into account the fact that we have equilibrium condition, then this resultant force, like projection on x, axis x. So this is our some resultant force F. So its projection on the axis x will be tension times sinus theta. So here, keep in mind that you also have angle theta, and theta tension times sinus theta minus electric force. Okay, according to this drawing, it will be different signs. So electric force will be along the axis x, and projection of tension will be in opposite direction. So it will be minus t times sinus theta plus electric force. And this is equal to 0 because it doesn't move anywhere. And similar, we can write for the y axis projection. In this case, it will be t times cosine theta minus mg equals to 0. So here we set these conditions for our stationary system under equilibrium conditions. So now how we can express this electric force besides Coulomb law. Obviously, we will come back to this. But now we can also express it from this triangular as electric force is equal to mg times tangent theta. So we see here, this is electric force, and we have the tangent theta is the ratio between electric force and mg. So from that, we can write the expression for the electric force. Also, we can determine what will be this distance a from the center position. So this can be done from this triangular. Here, we know that this side hypotenuse of this right triangular is L, and that's why we can write that A is equal to L times sinus theta. So now let us write the Coulomb law for the electric force. Electric force is equal, let's use here Coulomb constant, Ke is equal to 1 divided by 4 pi epsilon 0 times Q square, because we have the same electric charges, divided by r squared, so distance between these charges. So from here, we can express unknown parameter, which is Q. So that's what we would like to determine. So Q, the value, the electric charge, will be square root of electric force times r squared of distance between these charges, and divided by Coulomb constant. So going further, we know that the distance between charges is equal to 2a, like two distances from the center. So we can replace R by 2a. So it will be electric force 2a squared divided by k E. Okay, so now we need to replace by its values electric force and A. So electric force we can express with this first equation and A with the second equation. So let us substitute it in this square root. And we will get the following. It will be, instead of electric force, mg times tangent theta times 2L sinus theta square divided by KE. Yeah, so this is the final equation which can be used to calculate the electric charge Q. And keep in mind, please, when you're going to work on your homeworks and also late midterms, try always to lead your calculations step by step to the final equation, and only at this final stage substitute any numbers in this final equation, because this will definitely help you to reduce chances of some accumulative errors when you round some results step by step, if you calculate and round numerical values step by step. So eventually it will help you to avoid such situations when you accidentally can exceed over this +1 -1% accuracy, which is set by long kappa. That's really important, specifically while working with long kappa, that you have final equation and then substitute your numerical values in this final equation. So further, now we move further, and we need to introduce the concept of electrical field. It is very important concept in electrodynamics and in particular electrostatics, which we consider currently, because this is the way how electric interaction is realized. So electrical force, similarly as gravitational force, is a field force. So it means that electric force can act through space without any physical contact. So we don't need to have any physical contact in order to realize some interaction between electric charges. So what does it mean? That in the space around every electric charge, we have some electric field, this electric field defines how strongly it will interact, what a force will be exerted on another, let's call it test charge, which is placed in the next to the source charge. So we consider source charge as a charge which creates electric field around it. And then if we place some test charge next to it depends on the strength of this electric field. We will experience this test charge will experience certain electric force acting on it. So this electric field serves as some kind of medium which allows electrostatic interaction between charges. So electric field vector, so this is also vector parameter, E vector, at a point in space next to the source charge is defined as electric force which acts on some test charge located in this point of space divided by its by the charge of the test charge Q0. And this equation can be rearranged in more practical form, which quite often is used. So some electric force is equal to the charge located in electric field times the strength of electric field E. So this equation you definitely will use quite often to deal with different cases in order to calculate the electric force which will be exerted on any charge Q located in a point of space with electric field E. So if we consider in SI units, so the units for electric field will be Newton per Coulomb. However, this is not commonly used. Later we will introduce kind of accepted in the field of electrodynamics units. But for now, we have the units in the international system, which will be Newton divided by Coulomb. I guess we are almost running out of time, so we just gave the definition of the electric field. And further, we will continue already on the next lecture. It will be on Friday. We will consider more in details how electric field is, what is orientation of electric field, depends on sign of charges, positive or negative. And also we'll consider some cases of calculating electric field created by the system of charges, which are separated in space from each other. So in this case, we need to get some vector sum of the electric field vectors created by each of the electric charges. And then this is the approach how we can calculate the effective electric field based on the superposition of electric fields from independent, like separate electric charges. But that we will do already next lecture. Thank you very much for attention. If you have any questions, you're welcome. Also, you're welcome to ask questions on during our lecture on Friday if you have some concerns or don't understand some concepts. But hopefully everything will go smooth and we will be able to work efficiently.
Excuse me, Professor.
Yes, of course.
I have a question. On this week, will we have any like homework?
No, this week you don't have any homework. You will have homework starting from next week. It will be test homework, which will not be graded. So just you practice.
Okay.
And
So we will have homework next week, yes?
yes, yes.
Okay.
Okay, guys.
Okay, thank you.
You're welcome. No problems. Have any questions? Ask. That's very appreciated. Okay, thank you very much for attention. Have a good evening. Take care. Don't get sick. And see you on Friday.
Goodbye.
Bye bye, guys.